So thank you very much for all coming. I'd especially like to thank the organizers of the Bergamo Scienza. It seems like a really wonderful thing, and being hosted here in Bergamo, which is a lovely city. I'm also very happy to be talking about this topic, about teleportation. The title that I've actually given is slightly different from what was announced in the notices. I'll be talking about teleportation from science fiction to fact. Although, if people have questions, I might say a few words about quantum computation and the relationship. I'm especially happy to be talking about teleportation here in Italy, because in fact, in 1997, the very first experiment on teleportation, achieving teleportation, was actually carried out in Italy, in Rome. So for me, this is a special thing. But first of all, what can we mean by teleportation? We should try and define our terms to see that we're talking in the same language and that we understand each other. So suppose someone comes to you and they says, look, I've finally done it. I've discovered how to teleport. Well, you'd like to, understand what they're talking about. Well, let's try and give a definition. Well, we've seen, We've seen Star Trek. So let's try and take a stab at defining teleportation as some kind of instantaneous, disembodied transport. That's fine, except we already have a problem, because Einstein's theory of relativity, which has been backed up now by several decades of experiment, says that the fastest speed for anything, for any material object or any information for light, in fact, is itself the speed of light. So relativity says that nothing can go faster than the speed of light. Well, if nothing can go faster than the speed of light, then presumably also, if we could manage to do teleportation, it would also have to be restricted by Einstein's theory. So that would mean that we would want to change our initial definition to something which is closer to ordinary physics, and then we would say that teleportation is some kind of disembodied transport. Okay. That's fine. What do we mean by disembodied? I've been rather vague, and rather than trying to give a technical definition of it, I'll just rely on the view that we have from television, from Star Trek, for example. So, for example, someone, maybe Captain Kirk, is on their spaceship, and something happens and they disappear, and some information is transmitted to the planet, for example, where he's going to be reconstructed, and then he appears there. So some information is being transmitted, and there's no obvious way, the Captain Kirk isn't traveling in some little capsule, so he's traveling in some disembodied fashion. So if that's going to be our definition for what we mean by teleportation, then if we start to think about it for a second, we actually say, well, that's curious, because if I'm going to call that teleportation, then in fact I already have many examples of teleportation that I'm familiar with, if I think about it. For example, the fax machine. You take a piece of paper with your message, maybe your talk that you've been presenting, and you put it into the fax machine and gets scanned and sent to the other side, where a machine reconstructs it. And, out comes the copy of what you made. Or you might have the telephone, where you're talking on the phone, and the sound waves are picked up by a microphone, and they're converted into electricity. And then the electricity is converted into radio waves, and then, for example, with a cell phone, and then transmitted to the other end, where they're reconstructed as sound waves. So, similarly, we might have an overhead projector, or something a little bit fancier with the digital projector. I have the image on my screen, and in some disembodied fashion, the information is being sent through wires, and then it's reappearing on the screen over here. In fact, all of these are a little bit odd if I think about what's happening on Star Trek, because in fact every single one of these cases actually corresponds to a copying process. So the original remains behind typically. So in a fax, I have the original piece of paper with the information and I feed it through the machine and the original is still there. And a copy appears on the other end. Similarly with the telephone, if I'm talking on the phone, if someone is standing next to me, they will hear what I say, and it's only a copy of my voice which is produced at the other end. Similarly, I have the original, well, you can't tell, but I have the original here, and this is just a copy that's appearing up here. So, well, that might be a bit of a problem. So what's happening on, for example, in Star Trek? Are they doing the same thing? Maybe they are. Maybe what they have on Star Trek is a little bit like a photocopy machine, where maybe Captain Kirk gets on, but the light bulb inside the photocopy machine is set at such a strong level that it vaporizes him as it's scanning the positions and the velocities of all of his atoms. And so it needs to do that to be able to, and possibly also slice him apart, you know, to be able to get to the information throughout his entire body. Maybe that's what's happening. So that they're reading out all that information, and then when they've got the information, then they can send it in some disembodied fashion where it's reconstructed. Now, one curious thing that one sees on the television is that they don't seem to have a machine at the receiving end to reconstruct Captain Kirk, whereas in all of these other examples, so the overhead projector or the telephone or the fax machine, or indeed in quantum teleportation that I'll be talking about, we do need a machine at the other end. This we can't explain. So, but one thing at a time. Well, what about the original? So maybe it's the case that in Star Trek they're doing something like this. They're measuring the positions and the velocities of all of the atoms, and he's vaporized. But perhaps that's not necessary. Maybe if they used a much more gentle copying process, there might be no reason in principle why the original couldn't be scanned more gently and the original left behind. Would you want to do that? Would the original still have to pay taxes if there was a copy around? And what would happen to the soul? They're very difficult questions which we don't have answers to. But maybe they would lead to new fields of science if one could get to a stage of being able to do these sorts of things that we are doing now on elementary particles at the level of a human being, although that seems a long way away. So suppose we did want to try and teleport a human being. That seems like a lot of information, presumably a lot more than is in an ordinary fax. Well, just how much information? Well, it's hard to be precise, because perhaps we don't really know all the kinds of information that are really important in a human being. But we can at least get some estimate. For example, there was a project about a decade ago by the United States National Institute of Health called the Visible Human Project. And it was a very interesting project. What they did is they took a number of cadavers, so bodies of dead people, and they imaged them in many different ways. So they sliced them up and took photos, and they did what's known as MRI, nuclear magnetic resonance, on them. And they took many different images, all to a resolution down to about 1 millimeter, so quite small. And so for the entire body, they could store that on 10 CD-ROMs, so that's maybe a little over 1 DVD. But that's only down to 1 millimeter. Suppose you scale that down to atomic dimensions, to the individual atoms inside us. You might think that that would then contain all of the information. How much? So 10 CDs at telling you information down to 1 millimeter, if you scale that down to how much information you would need to describe what's happening at the atomic length scale, or down to atoms, then you would need around 10 to the 32 bits of information. So in other words, this much information here. It's so big, it's mind-boggling. In fact, It's such a big number that we don't really have a language. I mean, giga or tera or something like that, they're way, way, way too small. To give you an idea of how much information that is in just a single person, suppose we tried transmitting that with the best communication channel, the best optical fibers that we could conceive of building, then it would take about 10 billion years to transmit that much information. It would, I mean, that's phenomenal. Or similarly, if we packed all that information, we recorded it into CD-ROMs, and we packed the CD-ROMs into a big cube, then the cube would be roughly 1,000 kilometers on a side. So it's absolutely a huge amount of information. So doing this kind of scanning to try and extract all of the information in the human being down to the atomic level seems absolutely and utterly inconceivable from today's technology. It would be easier to walk than to teleport someone if we had a human being, if we had to do this. But there's a question: can we even copy down to the atomic level? Is that even possible? Maybe can we even do beyond? So, in other words, is this possibility, so making something like a fancy fax machine or a fancy telephone for quantum mechanical systems, for systems, as we would describe, which are acting down at the atomic level, which ultimately everything is made out of atomic systems. So is such a copying process possible? And the key problem comes in the early days of quantum mechanics in a principle called the Heisenberg uncertainty principle, which says that if you try and measure the positions of atoms too accurately, or any system too accurately, then the velocities can't be known very precisely. So in particular, if we try and locate the atoms down to an atomic scale, say for the hydrogen atom or just some typical atom, then they'll be uncertain in their speed to about 300 meters a second. And that's pretty fast. That's about as fast as a bullet from a handgun. So the very idea of even extracting that information, say about Captain Kirk, so precisely seems, again, something that doesn't seem like it's going to be possible. So maybe there's a problem. Maybe it's a good thing. Maybe we don't want to have the ability of copying a person and leaving an original behind. However, maybe it's not a problem. Actually, what did I want to... I guess I had a slide slightly out of sequence. Yeah. So maybe it's not a problem because, in fact, the thermal motion that, being at room temperature that we have is already quite a bit bigger by about a factor of 3 or 4 times from the motion or the uncertainty that's responsible from quantum mechanics, from the Heisenberg uncertainty principle. So that's an interesting question. Is it possible to have something like disembodied transport for a quantum mechanical system, given all of these issues, given the fact that the Heisenberg uncertainty principle seems to say that it's not possible, and maybe that the size of the thermal motion says maybe that you don't even need to do it, you don't need to worry about this at all if you wanted to try and teleport a human being, because you don't need to work down to that scale, or so it seems. But maybe you do, because that's only the motion of the particles. There's still a lot more quantum information. There's the atomic levels, and we don't know exactly what it takes to make the molecules combine together and sit in the motion that sit in the way that they do. It might be that the particular quantum structure is important. We just don't know. So let's try and ask the question anyway: is it possible to have some kind of disembodied transport for a quantum mechanical system? And to see why that might be especially difficult, another perspective from the Heisenberg uncertainty principle, we should try and go back to some elementary ideas about quantum mechanics. And this is actually echoing some of the slides effectively that we just heard in the introduction. So I'll go through them again with a slightly different perspective. So in particular, we want to consider things down at the atomic scale. So we might have an individual electron, so that's a single charged particle, or a single particle of light, or something like that. And it doesn't matter, we could use any system like this, any atomic system. And we're going to let it reflect off a partially reflecting mirror. So a mirror which sometimes will reflect the particle and sometimes let it transmit. It's given the name of a beam splitter, because the beam coming in might leave on one of two paths. Now, if we put a detector on those two paths at the output, and we have individual particles coming in one at a time on the input, then randomly we'll see a particle leaving on one side and then maybe a particle leaving on the other side. And the choice that the particles take, whether to go to detector 1 or detector 2, appears to be completely random. So it seems like this beam splitter is nothing but a place where a random choice is made. But apparently it's a little bit more subtle than that. If we bend the two output beams back together and then put a second one of these beam splitters so that we combine the original beam, which had been split into two, back into one, then something very curious happens. It's always possible to align this device so that all of the particles end up leaving just through one exit. So here they appear to be making a random choice at the first beam splitter, and at the second beam splitter, rather than making another random choice, they're actually combining together again, which is really bizarre. So you might ask the question, are the particles traveling in the upper branch or in the lower branch when they come, before they come here? So we can try and do an experiment. But before we do that experiment, we should ask what we might expect to see. Well, if they were individually taking one path or the other path, then the intensity that we would see at the output, the fact that one detector sees particles and the second detector never sees particles, should just be the sum, the combination of those two possibilities of the electrons, say, traveling on the upper path, combined with the intensity pattern of seeing electrons in detector 1 and no electrons in detector 2 from the electrons taking the lower path. So that means if we blocked one path, all we should expect to see is that the intensity on this first detector should get lower, and we should still see no particles on detector 2, if indeed the particles were individually taking either one path or the other path, but in some random fashion, as it appears to be from the description of the first experiment with the single beam splitter. What actually happens is that when we block one of the paths, it seems to mimic what we saw before. Rather than the intensity pattern getting smaller, rather than again just having fewer particles on detector 1 and no particles on detector 2, instead we have particles coming from a single arm here, and they seem to be making a random choice. So there doesn't seem to be any way of explaining this at all if we think that the particles are taking a definite path, either taking the path upward or taking the path downward. If we thought that, this would be impossible. The only other possibility, bizarre as it seems, counterintuitive as it seems, is that the particles, whether they be electrons or particles of light or whatever, are in some sense, and we don't know how to make it more precise other than to say in some sense, because we don't have another language unless we get technical, that the particles are taking both the top path and the bottom path. And that's strange, because that's not like anything else that we know. So quantum mechanics applies to the atomic scale. So here's a cartoon model, say, of an atom. So it has a nucleus, and there's an electron, say, in a ground state. Alternately, the electron might be in an excited state around the atom. So I've drawn some cartoon of the orbits here. But because it's a quantum mechanical system, the electron could actually simultaneously be in the two places, just like those particles in that interferometer I just showed you could be in one path or the other path, or simultaneously in the two paths. The same is true for a quantum system. the particles can be in two places at once. However, quantum mechanics doesn't just apply at the atomic scale. It's actually the theory for everything we have. It's the theory for chemistry, it's the theory for the cosmos, and everything in between. So quantum mechanics should equally apply to macroscopic objects, to people. And so whatever quantum mechanics says about the possibility of two microscopic particles being in two places at once, it is actually also saying the same thing about human beings or worlds or universes, which is really bizarre. So I already mentioned that thermal motion seems already to be quite big, and maybe it's not necessary to worry about quantum teleportation to teleport a human being because we're hot and we're wet, and so the fact that we're hot means that the Heisenberg uncertainty principle doesn't seem to be so important. But maybe it is. Maybe there are still subtle things. There are some scientists, very famous ones, like Roger Penrose, who believes that to really understand how the brain works, how the brain is capable of doing what it is, that one somehow needs to use quantum information. I'm not one of the people who subscribes to that, but maybe he's right. Maybe we'll find out one day. So let's ask the question, would it be possible to have some sort of disembodied transport for quantum systems? So one of the new realizations, or the new ways of describing the Heisenberg uncertainty principle, new ways of thinking about it, so it's essentially saying that it's impossible to accurately measure a quantum mechanical system. If we try measuring the position, then the velocity will be uncertain. If we try measuring the velocity, the position will be uncertain. If we try measuring through which path the particle will go through, then we'll end up destroying the state, and the particle will no longer behave as it had before, and no longer go through just a single path, as I showed you. And because it's impossible to make a measurement, that also means that it's impossible to make a copy. Why? Because if I could make a copy, I could just have a copy machine which just reproduces the original, and then I could do it again and again and again and again and again and again and make many, 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 many copies. And then with each of these copies, I could learn a little bit of information. So I could learn the position of the system from one and the velocity from the second one, and so on and so on, until I learned everything. But if I could do that, I would violate the Heisenberg uncertainty principle. So the way maybe to give a picture or an icon for a new way of thinking about the Heisenberg uncertainty principle is to say, not only is it telling us that it's impossible to accurately measure a quantum system, it's also impossible to accurately copy it. So here we have a little icon for what we call the Nocloning Theorem for quantum information. Classical information can be copied. That's why a fax machine is possible. That's why a telephone is possible, to make a copy of your voice. But quantum information cannot be copied. That's a problem because I'm here to talk to you about the experimental realization of quantum teleportation. So here am I giving you this introduction, telling you that it appears to be not possible. So let's see again why it seems like why it's a problem. So suppose we have some quantum mechanical input state, and it might be any kind of thing. It might be some state of electrons, or of individual particles of light, of photons, or it might be some larger quantum mechanical system. Maybe even one day something like a person. And we're going to give it to one person who will be the sender. And it's been traditional in the field to call the sender Alice. So it's her responsibility to try and teleport this quantum state. And she has a friend, Bob, who's going to be doing the reception and trying to reconstruct the quantum system. So why is this impossible? So Alice is going to take the quantum mechanical input, do something to it, possibly measure it, extract some information out, and she'll send that like you would, say, with a fax machine or with radio waves or whatever, just using an ordinary classical communication channel. She might even just use smoke signals. Anything is okay. And then Bob's job is to try and reconstruct the original. Let's suppose for a moment that was possible, that it was possible to accurately transport in this disembodied fashion the quantum information from Alice to Bob. Why is that a problem? There's a problem because someone might be listening in on the classical communication channel. We might have an eavesdropper sitting here. And whatever protocol, whatever Bob was doing to reconstruct the state, another Bob, an eavesdropper, could be doing exactly the same thing, using the information through this classical communication channel, which might be being bugged. So that would mean that if Bob was making a copy, an accurate copy of the original quantum state, then Bob 2 would also, the eavesdropper would also be making a copy, would also be reproducing the original. So there's a problem that the disembodied transport of quantum information appears to be impossible because the channel through which you're sending this disembodied information can be eavesdropped upon by anybody. And that would violate the Nocloning Theorem. So we've got a problem, because here am I telling you I'm going to give you a talk about the realization of quantum teleportation. Fortunately, in 1993, we discovered something really remarkable. We discovered that if you include an extra shared resource between Alice and Bob, this is really a bizarre quantum mechanical resource. It's called quantum mechanical entanglement, and I'll tell you a little bit more about it in a second. So it's something that Alice and Bob will share with each other. And if they have this extra resource, then this teleportation is possible. Further, because they're the only pair who have this shared resource, it doesn't matter whether someone else, whether a second Bob, is listening in on the classical communication channel, looking at the smoke signals or whatever that Alice is sending to Bob, because that's not sufficient, because they won't have this shared resource. And so it is possible to teleport a quantum state in a disembodied fashion, just like I was telling you about what quantum teleportation should be, but only with this extra resource of quantum entanglement. So what is quantum entanglement? We have a pair of systems, one at Alice's side and one at Bob's side, and they have to be highly correlated with each other, but much more highly correlated than any classical system we've ever seen. There are a pair of quantum mechanical systems, and they're simultaneously correlated in every possible way, which is a bizarre thing. The closest we can have to describing it in ordinary language is to use metaphor rather than use equations. And so there's a very nice metaphor from Charlie Bennett, who's at IBM and was one of the inventors of the teleportation protocol, which is that entanglement is a bit like a pair of perfect lovers, that even if you separate them from a great distance, they somehow know each other so well that if you asked one of them a question, maybe about something that they never heard before, about a topic they never heard before, and they've never heard their partner talk about, but you ask them this question, and you ask, what would your partner say if I asked her this question? And the perfect lovers would be able to tell you. It's in that sense that somehow it's like mind reading, even though they're separated from each other. So we have these quantum entangled particles which need to be shared between Alice and Bob, and once you do that, then it's possible to perform this quantum teleportation. It's weirder than science fiction in many ways. It's not instantaneous, unfortunately, because of relativity. And we certainly can't do it on anything as large as a human being or a Klingon at the moment. But it has some very amazing features. So, as I said, we can transport a quantum mechanical system through a classical communication channel, which is really bizarre because quantum mechanical systems are very, very fragile. That's what the Heisenberg uncertainty principle is telling us. If you try measuring the system, you destroy it. You can learn a little bit of information, but all the rest is gone. So, and a classical channel, well, anybody can listen in on that. So it's really surprising that you can transport something so incredibly fragile through something so robust. And that's one of the remarkable things about teleportation, and is one of the reasons why it's potentially the backbone for building a quantum computer, which I actually wasn't planning on talking much about. Also, to describe a quantum state, you actually need a lot of information. Yet the teleportation protocol, you only need to send a very few bits. So that's a real surprise. Similarly, once you share the entanglement between Alice and Bob, Alice doesn't actually need to know where Bob is. She doesn't need to know his coordinates, which they always require on Star Trek. They always say, type in the coordinates and then we'll teleport the person to that place. In quantum teleportation, Bob can take his half of the shared entanglement and be anywhere. He might be on Alpha Centauri, he might be on the moon, he might be next door. We don't need to know. The classical information we can broadcast everywhere. We can write out in smoke in the sky. We can put it in the newspapers. We can send it in radio signals to other planets. It doesn't matter. Wherever he is, so long as he finally gets that information, he can complete the protocol and reproduce the original quantum system. And there are many other things. You can also teleport the shared resource of entanglement itself, and that's also being achieved. And there are many technical things which make teleportation really fascinating. As I said, teleportation was first announced in 1997, and already within a few months in 1998, several groups, a total of 4, had already published papers demonstrating teleportation. I was involved with one of those groups. By today, there's already a dozen or so labs which have teleported single photons, whole beams of light, even the states of individual calcium or beryllium atoms. So initially, states of matter were only teleported a few microns, but now they've been teleported about a meter, whereas light's being teleported a distance of 55 meters, but through 2 kilometers of optical fiber. And in principle, there's no limit to how far teleportation can be done. Maybe one day we really will be able to teleport something, to a distant planet. As I said, even entanglement itself can be teleported. This is one of the early experiments, as I said, one of the experiments I was involved in 1998, and this looks quite complicated, but in hindsight, this now looks very simple. 1998, when teleportation was really announced in a big way, it made a big splash and was described as one of the top 10 scientific achievements in all fields of the year. And very recently, a group I'm working with used a much more complicated experiment to teleport this shared entangled resource. So those were the key things that I wanted to tell you today, that we've moved from something which, at least to some extent, is perhaps inspired by science fiction, teleportation. What we actually do is subtly different, in some ways perhaps disappointing, but in many ways actually much, much more surprising and miraculous than the science fiction writers ever knew. And, well, I've written a list of things here, but it really does open up a whole new world. Thank you very much.